go to A, B, and C, and then there are some weighting factors that could be, let's say, W1, W2, W3. And then this allows you, in principle, this you can think of it as a way to fit nonlinear functions. Essentially what this is doing. So therefore, artificial network in a nutshell, because I was told that there will be students here in the audience, I need to put some background, so the professors know all of this, but for the students this might be new. So this is what they call shallow feed-forward artificial neural network, can approximate any continuous function. There's some training data. You need to minimize a cost function, and then there are these links here between the input layer and the hidden layers here. And then if it is, typically there is one hidden layer, could be two, but some cases you can put three or more, and it becomes deep, because it's not like one hidden layer. And then there is an output at the end. So therefore, the data, imagine that there is, let's say, input 1, x1, x2, you assign some weighting factor, W0, W1, W2, and then the output is a function of these weighting factors in this manner, x1, W1, x2. But the function itself, phi, it could be of this kind, perceptron variant, which will be Heaviside function, could be linear, could be this kind of thing, or for this one here, for multi-layer neural network, this is very popular, sigmoids, hyperbolic tangents. So these are the nonlinear activation functions that they create a boundary in input space. So these are like classify them in A or B or C, ground state, excited state, etc. So this is what neural networks are doing. You get the input vector, you multiply them by some weighting factors, and you get an output given by some activation function, which you need to choose here. So therefore, and then essentially exactly at the end, you want to have some decision boundaries. You need to be able to classify, separate different groups, and then they can, in general, they require nonlinear decision boundaries. And then two layers input are not enough. You need to put one hidden layer, sometimes two, sometimes more. And then the standard one, you have one single layer, and is sufficiently powerful to approximate arbitrary nonlinear decision boundaries. And then if you add more, then you can get more complicated problems here. Exactly, so you need to find out which are the weights and the biases, but you need to do this by iterating several times. And then there is a penalty when you get the wrong prediction. And then here, okay, so we talked about this already, so let me just keep this on here. Okay, this is a standard unsupervised called k-means, is the k is the number of clusters. So you need to decide how to measure distances in this space. Could be Euclidean, could be Chebyshev, could be, there are different metrics. You choose them based on the one that can separate the boundaries better. This is an example where you can actually, at the end, you get this, any dot in this area is classified as red, here blue, here in green, because there are more commonalities among the green dots here than with the red dots and the blue dots. Or you can do, in some cases, you can do a rotation of axis, and then you can get, like you can get this case like a principal component analysis. You get the ground state and excited state in this manner here. Or you need to embed it in a higher dimensional space called manifold learning. So in this case, a nonlinear embedding, so you can have one cluster here, the next one here, the next one here, and these cannot be done in lower dimensional spaces. You need to do it in higher dimensional spaces. Exactly, the colors represent similarities, not labels, because there are no prior labels if you do unsupervised learning. Of course, you can take the higher dimensional nonlinear embedding and flatten it out in 2D, trying to preserve similarities, distances between data points. Okay, let me do one example here. Okay, so we did an example on approximate autonomous quantum error correction with reinforcement learning. More details are here. This is a very technical paper because quantum error correction is just is a whole field by itself with massive amount of jargon and machine learning also. I'll give you the main idea. If you want details, no problem. I can inflict upon you an entire talk, 60 slides afterwards. But these are like, requires many definitions, and I'll be glad to to show them afterwards. I'll show here the main result. It was published recently, and people like it because typical quantum error correction, you need to move many knobs. You need to make measurements, but every time you make measurements, you're messing up the subject, the system, so you would like to do it autonomously. And this is by interacting, by controlling the way you interact with the environment. Okay, it's a very technical field, it's a massive amount of jargon. I'll do a brief summary and then move on to other results to give an overview. So therefore, the bottom line is the following. Once you do the calculation, you want to know if the fidelity is high or low as a function of time. And then the comparison, the benchmark, is often called the break-even line, which is this one here. So therefore, a famous one called binomial code can get better than the break-even up to a certain time, and then it gets slightly worse. There are other ones we call square root of 3 code, which is doing better. And they were able to do actually much better, at least for a certain time. Initially, it's a bit worse, and then crosses 1, 2, 3 very quickly, and then it gets much better. So people like found that this is what we call the RL code, outperforms binomial code if there is a single correction jump operator. This is a technical thing, but the main idea is that to protect the logical qubits by engineering dissipation. And we do this to avoid the necessity of frequent, error-prone measurement feedback loops. Every time you put measurement feedback loops, you're messing up the system. So we'll say, let's avoid this. And then there are some spaces called Bosonic code spaces where the single photon loss represent the dominant source of error. And these Bosonic code spaces are promising candidates for autonomous quantum error correction due to their flexibility and controllability. The people are right now studying these codes now. And then the downside of these Bosonic code spaces that it's based on the exact implementation, so the Knill-Laflamme conditions, which are difficult to implement in practice. So therefore requires multiple interactions, control fields. Experimentally, these are like messy. So we proposed a Bosonic code with this approximate autonomous quantum error, but relaxing these conditions, these Knill-Laflamme conditions. And using reinforcement learning, we identify the optimal Bosonic set of code words, the basic sets, which are composed of, these are states that have 2 photons or 4 photons. And as we show this code, this Bosonic code successfully suppresses single photon loss, reducing it to an effective dephasing process that does much better than break-even threshold. So it provides a good building block towards full error protection. So we're excited about this. The referees are also excited, so let's see how this can be implemented in the future. But this is one set of recent results applying reinforcement learning. There is another one doing, okay, in this case, we're doing different kind of techniques, including deep neural networks. So the goal here is to do a density matrix reconstruction with deep neural networks. And the details are on this work here. These are called conditional generative adversarial networks. These were developed many years ago, essentially when people beat the IBM computer on chess, the next goal was to beat the Go player. But Go is far more complicated than chess. So therefore, the training process would have been too long. The way to make the long training process shorter is to put 2 neural networks competing with each other, training each other. The idea is that one of them is called generative, another one is checking. So there's a metaphor, is like, imagine that the goal is to do counterfeiting bills, for example. So therefore, the generative model is trying to generate counterfeit bills, but the discriminator is saying, no, this one here doesn't work. This is problem, this one here doesn't work. And then the generator is improving the counterfeiting bill until finally is able to convince the discriminator that the counterfeit bill is actually is a very good copy of the original one. So in this case, there are 2 networks competing with each other. And this is the short version here. If you want to see all the bloody, gory details. There are something like almost 40 pages long, this one here. They were published at the same time on